The second session is on common sense knowledge, and it will be chaired by Keith. By Keith Burkhardt. So Keith Burkhardt is a research scientist at the Information Sciences Institute, and the speakers on this session will be. So we have 4 speakers again. Pedro Sekeli will be talking about dimensions of common sense. Marjorie Friedman talking about learning common sense. Muhao Chen will be talking about robust knowledge acquisition, and then Yolanda Gill about crowdsourcing common sense. So I guess I'll just hand it over to Keith at this point, and we can go from there.
Thank you. Just to do a little bit of housekeeping, I just want to mention, of course, that questions will be answered at the end of the session, and that I'll be giving a warning to panelists when their presentations take about 8 minutes, just to make sure that everything is moving at the appropriate clip. So with that, I think we can start with the first speaker, who is Pedro Sekeli, Research Associate Professor of Computer Sciences, of Computer Science and Principal Scientist and Director of the AI Division at the Information Sciences Institute. So with that, Pedro, please take it away.
Okay, thanks, Keith. So sorry, I have a bad cold after getting all my shots, and so apologies if my voice comes across badly. So next slide, please. So the work that is in this talk is a summary of a paper called Dimensions of Common Sense Knowledge. Philip is the first author in this paper, and actually kind of the engine behind this work. So next slide, please. So a definition of common sense knowledge we gave in the paper is that it is information that humans typically have that helps them make sense of everyday situations. Next slide, please. So here is our examples of common sense knowledge about food found in many different sources. So in ConceptNet, we see that food is capable of going rotten, that when a person bakes a bread, the effect is to eat food. When somebody makes something that is food, it causes or enables somebody to eat something, and so on. So many different sources have all kinds of knowledge about food that we can consider common sense knowledge about food. Next slide, please. One interesting thing is that only the first group of sources are actually labeled, or people who created them so thought of them as common sense knowledge. But what is commonly happening in the field of common sense reasoning is that people look at other sources for finding common sense knowledge. So there are the large knowledge graphs like Wikidata, lexical resources like WordNet. We used Visual Genome as a source of common sense knowledge, and of course, the language models. And we see, and we see that the number of relations in these different sources are very disparate. Some of them have only a very few relations, whereas others have thousands of relations. Next slide, please. So the research question that we posed in the paper is, can we consolidate the sources of common sense knowledge in some way, even though they are so disparate? And, is the consolidated knowledge useful in downstream tasks? So what we did is we grouped all the relations that we found in all these different sources in 13 dimensions of common sense. And then we measured the overlap and gaps, and then did experiments on how useful the knowledge in the specific dimensions is impacting downstream tasks. Next slide, please. So here are the dimensions. 13 dimensions with some examples like lexical knowledge, food is a nutrient, similarity, food is similar to dish, distinctiveness, food is opposite of non-food, taxonomic, part whole, you find food in the minibar, spatial, food is usually close to a plate, who creates it, what is the utility, what are the goals and desires that people have around food, qualities, comparative, temporal, and then finally another group that's just a catch-all for anything that we could not put in the first 12 dimensions. Next slide, please. And so we looked at the sources, and we see that some sources have common sense knowledge in all dimensions, for example, ConceptNet and WebChild. Wikidata has also knowledge in almost all dimensions, but very small amounts. And then the other sources really focus on specific dimensions. Next slide, please. So we wanted to see whether the dimensions of common sense knowledge align with the language models. And what we did is we lexicalized the triples in Roberta, and then created a sort of Disney diagram, and we see that even though there is some clustering, it is very noisy. Some of the dimensions seem to overlap a lot in the language model encoding, and we think this is because the language model takes into account the nodes in the triples, not just the relation in the triples. Next slide, please. So the impact on common sense downstream tasks. So we focused on two tasks, common sense QA, and you see an example question there, and social IQA, where you are giving a little context, a question, and then multiple choice answers. Next slide, please. So what did we do? So what we did is we first converted all common sense triples into questions. So you see the question that we generate at the bottom, losing weight is for being healthier, embedded software, or buying things at a store. And we did this for all the knowledge in all the sources. Next slide, please. Then, using all these questions, we pre-train a language model by dimension, as we're interested in knowing the usefulness of each dimension for the downstream tasks. And then we evaluated in the common sense QA and the social IQA. And what we found is quite interesting. We found that using all the knowledge does not produce the best result. So at the bottom, you see all the knowledge, and it doesn't always produce the best result. So for the common sense QA, the utility knowledge is the most useful. And for the, the social IQA, the temporal knowledge is the most useful. And at least in the social IQA, all knowledge is the second best result. And we see that the differences between the dimensions are quite large. This was kind of the main finding of the paper, that different dimensions are useful for different benchmarks, and not unexpected, but the differences turned out to be larger than we thought. Next slide, please. So the summary is that there are many disparate sources of common sense knowledge. We came up with 13 dimensions as a framework for integrating the knowledge. Some sources cover all the dimensions, some sources cover single dimensions, and they can be critical in the downstream tasks. There is little overlap across sources. And partitioning of common sense knowledge along dimensions seems to be useful to try to focus on downstream tasks. And interestingly, single dimensions are more useful than all knowledge in the downstream tasks. Thank you.
Thank you, Pedro. With that, let's go to the next speaker, Marjorie Friedman, Marjorie Friedman, research team lead at the Information Sciences Institute, who will be discussing learning common sense. Marjorie, please take it away.
Hi, so I've subtitled this as a machine with a goal of an average adult. Next slide, Keith, or Philippe, sorry. Before we talk about how we learn common sense, I think it's worth kind of building on some of what Pedro just said about the various dimensions of common sense. So I think we typically think about common sense as things you expect a person you interact with to know, things that help us interpret and interact the world around us, but are assumed so nobody tells us. But that's a pretty general definition. And so this includes really what children learn. Right? But when we're interacting with adults, we don't expect them to behave like children. And as we're building AI agents, we often want them to behave more like adults than like children. We expect people to know cultural norms. We expect certain facts to just be common knowledge. So if I say Paris, you're going to bring up France in your mind, probably. We expect people to understand processes, so how to plan a trip, the steps that are involved in that trip. And we also expect some amount of axiomatic information. So city names are not unique. So even though Paris, France comes to mind first, if you do lots of information extraction, as I do, Paris, Texas doesn't seem all that unlikely because you've seen it as an example a bunch of times. And so when we're trying to learn common sense, we're really trying to learn lots of different types of information. Next slide. And so why do we want to learn this common sense from an AI perspective? Well, AI needs common sense to both accurately interpret the world the same we do, and to serve in a useful collaborative capacity. And so if the AI is constantly telling you things that you already know, makes it less useful, even if it's correct. But codifying common sense is hard. We're often not aware of its axioms until they're violated. As you saw in Pedro's slides, these resources that have tried to codify it are very big. And this element of local common sense means that it does change, that the common sense is impacted by your very specific experiences and what you expect people who have experiences like you to know. And so learning lets agents evolve with their environment. And these are just examples where AI does something like placing Paris on a map where some amount of common sense is expected. Next slide. So how do we go about learning common sense? Well, the approach and data are often influenced by what aspect of common sense you're trying to learn and how you want to use that information. And so Pedro gave very concrete evidence of these different dimensions behave differently. Sometimes one is much more important than the other. But we can learn both from these crowdsourced knowledge resources. So we can automatically extend resources like Wikidata, like WikiHow, like ConceptNet. And in fact, several of these resources were built in part through machine suggestion, kind of in a human-machine collaboration. And we can also learn from things that we observe. So by reading the web, by looking at the videos on the web. Two examples of approaches that people take are to try to automatically transform data directly into axioms. And so I have, there's a canonical example of that on the next slide, but kind of doing information extraction or labeling an image with the red apple, letting you translate that into apples are red as an axiom. And we can also try to learn common sense in these machine interpretable spaces. So with embedded knowledge. Next slide. So in the context where you want to learn axioms, or facts more than axioms, you're learning to label. And so we often take tools like entity labeling, relation labeling, event extraction, and apply them to, here my examples are text. Similar approaches are used with images to extract information, where we say, Paris is located in France because the first sentence of the Wikipedia article tells me that Paris is a capital city of France, and that I know that that capital city prose represents a located in relation. There are two limitations and challenges to highlight with this approach. So if you go to open domain resources, much of what's represented in them is going to be represented in existing already curated resources like Wikidata. And much of what counts as common sense is assumed and therefore not written. And so Paris will be described as the capital of France or located in France some of the time when it's mentioned, but not all of the time. But this approach of learning facts can be used to extend existing resources with new information, especially if you're trying to localize your notion of common sense. Next slide. So a different approach is to say that the large language model, when it has read all of this data, has learned common sense associations. And so here, I'm not going to dive into how one builds these large language models. I'm going to say you have one. It's giant. And we are going to grab it and query it via question answering, via entailment, via generation, to try to grab the common sense information that that language model has learned via association. And the caveat here is that knowledge will be biased towards that which is common. And so you're much more likely to get an answer for Paris, France than you are for Paris, Texas. Next slide. So you heard about an example of doing this in a project where Emmanuel and I collaborated earlier today, where our goal is to build up a library of script-like information, build up an understanding on the machine side of what it means to do some activity like planning a trip. And so we initialize with something like 1 or 2 steps in the buying a trip sequence. And then we use our ability to probe these large language models to fill in the middle, to give us suggestions about a number of things that a person might call to mind if you told them that you were planning a trip, and it would be considered good responses. Next slide. And so building on that and connecting back to these structured resources as an additional way to learn and access common sense, you can ground this language in the structured information to provide rich access to symbolic knowledge that may or may not have been learned if you were just reading data. And so here, I've labeled my go to hotel or motel event as a transport, which has a link to Wikidata. So it's Q7590, which pulls up 2 axioms, one of which, neither of which is probably at the tip of your tongue, but both of which you would expect a person to be not surprised by. So one of which is that transport is an intentional activity, that somebody decided to do the transporting. The second being that an effect of transporting can be pollution. And so if you're asking what are the outcomes of transportation, certainly somewhere in your long list of things that happen is pollution. And so that is the end. Thanks, Keith.
Thank you. All right. With that, let's go to the next speaker, Muhao Chen, a research assistant professor of computer science at USC and a research scientist like myself at the Information Sciences Institute. He'll be discussing robust knowledge acquisition.
Okay, thanks, Keith. Next slide, please. Yeah, so I'm going to have some quick slides talking about our works on the topic of knowledge acquisition from my group. So we know that AI always involves understanding different relations of concepts. For example, in question answering and semantic search, we expect the machine understand different relations of entities, events, or phrases, terms, or different concepts. And also in e-commerce, similarly, we should expect the machine understand the properties and relations of different products. And in computational biology, it's always about the interactions of different molecules or biomolecules, or more specifically, relations of diseases and drugs. So, constructing those kind of structural knowledge, although it's helpful, but super costly. So we have been working on different knowledge acquisition models, which represents the automated process of acquiring, extracting concepts, relations, the structural representation from unstructured text. Yeah, next, please. So, however, currently, knowledge acquisition systems or models, they are far from being robust. For example, actually, there are they have different kind of fragility in both learning and the inference phases. For example, in learning, we know that annotating this kind of structures involving both lexical concepts and also relational structures on the document, it's actually a very hard to annotate, hard to articulate annotation task, which means that necessarily we are dealing with noisy and also incomplete training data here. And also we know that, knowledge is super diverse. So we are dealing with an ultra diverse label space. So for each label space, naturally we expect that the learning resource is very low, or, even you deal with lots of one-shot or few-shot cases. And in inference, on the other hand, when we apply a well-trained knowledge acquisition model in application, we know that it's very likely you will see data which is invalid, so that you should expect the model to extract nothing from it. So in that way, the question will be, how do we identify those kind of out of distribution inputs that we haven't seen in training? And also, on the other hand, in the inference phase, new knowledge may show up, new types of knowledge may show up. We may expect the model extract unseen or freeform labels, but the question will be, if we train the model as a closed domain model, how do we handle those unseen and freeform labels, right? That's another critical challenge in inference. And also on both learning and inference, it's always challenging to talk about how do we ensure, for example, we know that relations, among those relations, they are also related. They are ensured by different logical constraints, symmetries, transitivity, conjunction, implication, and negation. So how do we ensure the global consistency of extraction in both training and the inference space? So those are the 5 problems we have been tackling recently in our publications. So next, please. Yeah. So in general, in order to improve the robustness of knowledge acquisition models in both training and inference phase, we have published several works recently. For example, one EMLP paper this year. Here we investigated one co-regularized knowledge distillation model, in which actually framework in which we are able to train 2 or more models of the same structure, and then this helps the model proactively identify possible noisy labels, which the models do not agree on, and then lower the impact of those potential noisy labels during the training. And we're able to show that even during the training time, we don't know which part of them are noisy, which part of them are not. It is able to obtain very good performance on those widely used benchmarks for both lexical knowledge acquisition and also relational knowledge acquisition. And also we do see that when the training data is more noisy, we're actually able to gain more performance gain in comparison to vanilla, protein language model-based knowledge acquisition systems. Yeah, next, please. So on the other hand, in order to enforce robust inference with automated out-of-distribution detection, in another EMLP paper of this year, we also investigated a new way of using margin-based constructive learning plus Mahalanobis distance measure to let the model perform unsupervised out-of-distribution detection, so that the model is able to just see in distribution data, but during inference, it is able to sensitively identify what kind of data that are unseen in training. And we are able to achieve near perfect performance on the out-of-distribution detection data contributed by UC Berkeley, on which they mixed 20 different tasks into the same data set. But you can alternatively treat one task-specific data as in distribution, and the model should identify all the data from the rest 90 tasks. But of course, the rest 90 tasks, those data you haven't seen in training. Yeah. Okay, next, please. In addition, how do we ensure that when you have a structural knowledge acquisition system, it is able to give you globally consistent extraction, so that you don't have multiple relations on the edges, they are contradicting with each other. So towards this end, in one EMLP paper last year, we investigated a way of, first we convert different logical constraints among relations, including symmetry, transitivity, conjunction, implication, and negation into different forms of product T norms. And we combine those product T norm loss functions together with the task-specific gross entropy function. And learning those together, we are able to ensure globally consistent extraction with enforced logical constraints if we have already manually designed different types of logical constraints. Yeah. Okay, next please. Then after that work, we realized that if you have a very large label space of relations, then there are really lots of constraints you need to manually design. Also some of them are hard to articulate, but in general, if you have, let's say, k different relations, then actually the space of the constraints are actually exponential of k, so which is super costly. So in another EMLP paper this year, we actually discussed a way of automatically induce constraints from the training data of relation extraction. We actually trained a rectifier network into regressor, and this rectifier network will iterate all, you can call those triangles in the ground truth extractions of the training data, and it will decide the truth values of each possible constraint, and later we can enforce those automatically captured constraints into the previous framework we just shown, and still ensure the knowledge acquisition system to give globally consistent output. Also, in this case, we do not need to manually design any constraints. Okay, next, please. Okay, so lastly, most recently, we are also working towards the goal of dealing with open domain, free-form, ultrafine knowledge acquisition, in which we allow any kind of labels to appear during the inference time for which we haven't seen them in the training. And also typically in this situation, we are dealing with thousands of labels. For example, in the ultrafine entity typing benchmark, we have more than 6,000 freeform types. So this is actually going to be very difficult for any kind of knowledge acquisition model to perform inference. So towards this kind of challenge, really it's about generalizability and also adaptiveness of fine-grained labels and also unseen labels. And our general solution is we borrow indirect supervision signals from other tasks, for example, natural language inference. So in this paper, which is in press for TACO, actually the first author of this paper is an undergrad student in my group. So we developed a new system which leverages natural language inference for ultrafine entity typing. So specifically, we treat each entity mentioning sentence as a premise of the NLI. Then we convert each type label as a hypothesis in the NLI. And on top of that, we perform a learning to rank. We let the model rank correct type description over any incorrect negative sample type descriptions. So here we have three benefits from this system. So first of all, we can borrow strong indirect supervision signals from pre-trained NLI in comparison to previous models, which just use language models as feature extraction, but they do not have any pre-existing inference ability. That's benefit one. The benefit two is that we can allow any unseen label to appear in the inference phase. We can freely convert them into a natural language description that serves as a hypothesis. Also, in comparison to previous systems, which is to train a multi-way classification on language model output. In those situations, if you have unseen labels, the model has to be retrained, otherwise you cannot use it. And also, more importantly, our system obtains very excellent transferability. We are actually able to outperform the state-of-art supervised systems on Ontonodes and Figer when we just perform zero-shot transfer of our system that is trained on UFET. So this is actually a very awesome results. Okay, so yeah, this is a list of our recent contributions on knowledge acquisition. We have some works which I already mentioned. We're also working on other problems like how do we consolidate open domain knowledge acquisition, and how do we transfer knowledge among different languages, and also how do we debias knowledge acquisition so we can let it have less keyword bias. Yeah, so on and so forth. Yeah, so we do have upcoming information extraction tutorial proposed in NACO this year. We'll talk about robustness, transferability, indirect and minimal supervision, and also how do we support cross-modality knowledge acquisition, and also how do we enforce known knowledge to acquire unknown knowledge. Yeah, thanks.
Great, thank you, Muhal. So with that, we'll move on to Yolanda Gill. And I'll also briefly mention that feel free to put questions and answer questions in the Q&A chat, and we'll answer those at the end of the talks. All right, Yolanda, please take it away.
Thank you, Keith. I want to talk about an alternative way to collect common sense knowledge through crowdsourcing from people. And it's an alternative to acquiring common sense knowledge from text, as we have been hearing here. In this talk, I'm going to take you back a few years and then come back to the future. We started this work. I traditionally worked on collecting knowledge from experts. And I started this work as a collaboration with Tim Chiklovsky, who had just completed a PhD thesis at MIT with Patrick Winston on learning about objects in the world. And he had developed analogy and similarity metrics so that if the users had already taught the system about books or magazines, then it should be much easier to learn about newspapers because they have so many commonalities. So he exploited these similarities to make the acquisition of new knowledge very efficient. And we ventured together on expanding this to acquire new kinds of common sense knowledge. So I want to talk a little bit about the challenges in acquiring common sense from volunteers. Next slide, please. So one of the things that we worried about is how could we draw volunteers to actually contribute knowledge, and how could we minimize the training that would be required? We were not sure that they would be able to contribute useful things. Another big question was, how did we guide them towards topics or areas of common sense that were of interest to us? Also, we were worried about the quality of the knowledge. How can we best structure and organize the knowledge? If you acquire piecemeal knowledge from volunteers, then how can we make sure that it amounts to interconnected structures that we could use? And then finally, how do we validate and refine the acquired knowledge? And I'll come back to add more challenges at the end of the talk. Our work was motivated by assisting people with to-do lists, and we realized very quickly that this could not be done without common sense knowledge. So this is where I'm taking you back in time. We were funded by DARPA as part of a project called Personalized Assistance That Learned. This was a project to help people in office-like environments by providing assistance. This is the program that gave you Siri. So this is pre-Siri. And we were looking at users' to-do lists and thinking, how could we help them? Could we help them by automating some tasks? For example, if they wanted to set up a meeting or reserve a room, or assist them with information, getting advice from others, giving information from the web. So everything centered around to-do lists. Next slide. So the kinds of tasks that are in to-do lists are very, very interesting. We had some examples from office environments that we collected. So they have a very unusual structure. Sometimes they don't have a verb. Sometimes they are questions. Sometimes they use many different ways to refer to the same task. Sometimes they're very incomplete. They're just a note or a reminder. They're very ambiguous, and many times they include personal items. So we did a lot of studies of what the to-do list looked like and what kind of knowledge would we need to supplement them. Next. We also collected to-do lists from other contexts outside of the office. So we did for web applications, and we did one in Facebook, and the entries were a lot more diverse, as you can imagine, and much harder to automate or assist, but we could do it if we had enough knowledge about what the tasks involve. Next. So we started to work on what kind of common sense knowledge would we need about tasks, and it mostly revolved around the objects that would be involved in doing a task. You have to have them in order to do that task. We realized that we needed paraphrases of the same task so that we could understand what the user was saying, decompositions of the task so that we could anticipate what the user might need to do, or give them an advance warning about that subtask, relations between tasks, particularly temporal, and then the durations of the tasks. Next. So we actually collected a lot of very useful statements about objects, about tasks in office environments, and also about verbs that I'll tell you about. So we were very focused on the quality of these statements, the usability of these statements, and how to validate them. Next. So first, we would use templates to focus the acquisition. So we had prompts that ask people to tell us about different types of events and types of objects. Next. Then we would expand that, what we collected through those templates, with additional information. So we would prompt users about related knowledge. And we just heard in a talk how to get this related knowledge today from language models. Next. And then we worried about validating the collected knowledge. So for example, a volunteer might enter that you need a paper plane in a meeting. Next. So we designed very carefully how to do these prompts. We learned about objects and tasks. We had a lot of interest in anticipating possible failures and having repairs, and also to learn paraphrases about these tasks. And what you see on the right are some of the principles that we were following to design these interfaces. So always guiding through templates, providing examples to give the user an idea of what we were looking for. We would always process what they told the system and then follow up with more questions that gives them an idea that they're actually being useful. We validate through other users. We proactively follow up to expand what we know. And there's always some type of knowledge that we're after in each of the templates and each of the prompts. Next. The templates are designed so that we know how to follow up with other questions. We would give them scores and points. That was very popular. We told them when other contributors agreed with them. So we had a fair amount of work on how to keep these volunteers engaged. Next. So actually, we were able to enlist thousands of volunteers. If we raffled a t-shirt at the end of the month, there would be a big spike on contributions. So somehow freebies really mattered. We also had a museum exhibit where that it toured many cities, and it was called Robots and Us. And so people would sit in the booth and teach the system common sense, and then go home and go over the web and contribute. Next. We also worried about extracting duration and the ordering of activities. And not only we did this from contributors, from volunteers, but also from text, and so that we could predict that lunch meetings would last for an hour, how long would presentations last, and so on and so forth. And we started work on comparing what we got from volunteers with what we extracted from text. Next. So this work on common sense led us to focus on a particular side of common sense, which is factual encyclopedic knowledge. And so we designed the system called Shortypedia, together with Denny Vrandicik when he was here at ISI, to collect facts that are stated in long sentences and harder to process language in Wikipedia. So we designed Shortypedia, which was the predecessor for today's Wikidata, which you've heard about in other talks. So I'm proud to have started this effort from ISI. Next, we use these techniques as well to crowdsource scientific vocabulary. So this is kind of common sense in a particular scientific discipline. And sometimes we discover what's not so common that they know about. So this has been very successful work. Next. So to close, there's many challenges in crowdsourcing common sense knowledge. We were able to demonstrate that we can retain and manage volunteer effort and collect useful responses. But we'd like to continue to explore how these techniques connect with text extraction and to use all of this knowledge in practical applications. Thank you.
Yolanda. So what I was just told by Philip is that we can go on as late as 11:05, and that'll still give everyone 10 additional minutes for break. So I would like to start with some of the people who posed questions from the Q&A. So Carlos asks, so first off, this to everyone, Muhao, Yolanda, Pedro, Marjorie, feel free to answer these. Carlos asks, I would like to ask how common sense takes into account, for example, cultural, social, religious, age, ethnic, etc., gender differences. So how do you take into account, like, maybe context of that sort? Maybe we can start with Yolanda.
Yeah, I think we have some talks later on this particular topic. For us, it's one of the things that we notice, that there's a lot of nuances to common sense knowledge, a lot of exceptions. People will make different determinations. So it was one of our challenges with volunteers. So for example, you know, is film part of a camera? So depends on the type of camera that you're buying. And even if it's a camera that uses film, when you buy it, it is a camera, but it doesn't contain film. So when do you say that a camera contains film? So a lot of the statements depended on the context, and so there's a lot of personal criteria that people were using to answer our questions. It was a challenge. Yeah.
Thank you, Yolanda. Any of the other speakers want to answer this as well? All right, with that, we can move on to Marjorie. There's a question for you from Bart, saying, when using language models, how do you go from association information to causal relationships?
I mean, I think you don't necessarily. I think there's a question of, for the thing that you are trying to use common sense for, do you want that causal relationship, right? And so there's certainly work out there trying to discover and better model causal relationships. I wouldn't claim that the language models have them, but the common sense is actually something that we don't necessarily access the causal relationships ourselves. And in some cases, in my Paris is in France, which is, a fact, but what is the causal relationship there? It just kind of is. And so I think, for certain contexts, that limitation of association is really important, and a reason that you might want to access common sense in other ways. But for certain contexts, the absence of causal information is just something to be aware of, that you don't have access to it.
Thank you, Marjorie. I will actually ask a question now for Pedro, so that we can actually have questions that are for, roughly speaking, each speaker. I wanted to spread it out a bit. So the question I have for you, Pedro, was how do you address the potential different contexts that may affect the different common sense KG data sets? For example, there's in your paper, you discussed the polarity of food, which could be positive or negative for cold foods. For example, you don't want to have hot ice cream, but you might want to have a hot, fried chicken or something like that. So it may depend on the person or the data set. So how do these differences impact the utility when blending knowledge graphs? Pedro, you're muted.
Yeah, so I think this is related to the question that Yolanda answered. And I think one of the things about common sense knowledge is that it is never always true. So I think that's kind of the critical aspect of common sense knowledge. It is true most of the time, but you can always come up with a context when it's not true. And I don't think we have figured out how to represent this symbolically. So this in the symbolic knowledge graphs is done very poorly. I mean, the theories of you're representing contextualized knowledge are very complex. And this is all never done in the practical knowledge graphs. And I think this is the place where language models are so powerful. And so, somehow figuring out how to extract the context from the language models to know when a common sense fact is really a factor and it doesn't apply is kind of the critical sort of research question.
Thank you. And so now there's another question from Henry. I believe this has not been answered before, which is directed towards Yolanda. When learning scientific vocab, was there a problem with words that both a common sense and that have both a common sense and a technical meaning, e.g., tree, the plant, tree, the data structure?
Interesting question. I think when we create these what I would call common knowledge in technical areas, it's not necessarily common sense, but it's common knowledge that everyone in that maybe subculture shares. We find that there's a lot of ambiguity in the way that they use terms and they throw them around. So they have to kind of agree to pin down the meaning of the terms. And so the ambiguity is because they use the same term for many different things and they're never very precise. So they're kind of working together to negotiate how to pin down those meanings. And I wonder if those problems would map to common sense problems where we all think a certain way, but maybe that's not the case. So maybe we think, or most people think that there's only one Paris, using Marjorie's example, there's only one Paris, but actually, we can debunk that belief by showing that there's others. So very different kind of ambiguity problems there.
Great, thank you. I believe that's it for questions, and I think that still gives people plenty of time to take sort of a biological break, etc. So with that, I just want to thank everyone for their presentations, and also all those who ask questions. These are really interesting questions as well.
Okay, many thanks to you also, Keith, for leading this session and for keeping the discussion vibrant and exciting. So we'll continue in 12 minutes at 15 past the hour. I'd like to say that we have a keynote by Tomer Ullman, which relates to this topic. Hi, Tomer. Which relates to the topic of knowledge acquisition, but from a very different perspective of knowledge acquisition from infants, which is, we always cite how common sense is the common knowledge that even young people have. So I think this is a great segue going from from all of these talks on computational acquisition of common sense to basically learning how children actually do this, hearing that from an expert. So yes, so we resume in 11 minutes. See you then.